instrumentation and application of high performance liquid chromatography, HPLC and HPLC-MS. So before going to that, we'll also talk about a little bit of chromatography to give the background so that it is easier to understand. Now I'll dig straight away into the, sorry, I'll dig straight away into the presentation now.
Yeah,
So,
sure.
yeah. So let's talk about chromatography. So chromatography is uh, basically chromatography comes from two words, that is chroma, which means color, and graphy, which means to write. So chromatography as a whole.
Excuse me. Dr. Saurabh, we can't see your screen.
You, uh, just give me a second. Let me. Uh, I okay. So is it visible now?
No, not yet.
Not yet. Okay, looks like I'll does it work now?
No, sir.
Okay, something. I don't know what's going wrong.
Now we can see your screen, but no presentation.
Okay, okay. I'll pull up the presentation.
Yeah,
Now,
right.
yeah. And I don't know what this box is. I'll just drag it down. Yeah. So, so we'll start with chromatography. So, chromatography comes from two words, that is chroma, which means color, and graphy, which means to write. So as a whole, chromatography basically means color writing. Now, this technique was first carried out by a Russian scientist, Michel Swart, in 1903. And what he did was that he eluted a petroleum ether plant extract. So what exactly is a petroleum ether plant extract? You take a plant material and then you add petroleum ether to it, and you mix it, and then you filter out or pour out, decant out the petroleum ether out of it. After that, you filter that petroleum ether, and then you run it on a column. So what he did was, he took this petroleum ether plant extract in a column which was filled with a stationary phase, which was packed with calcium carbonate. and he used liquid hydrocarbons as mobile phase. So what exactly is a stationary phase and a mobile phase, that I will tell you in a while. It's there in the slide. So there he separated three components. So first component was xanthophyll, which was yellow in color, and then carotenoid, which was orange in color, and chlorophyll, which was green in color. So this is how it all started. So now if we talk about the definition of chromatography, so chromatography is a purification and analytical technique that is used for separation of component dissolved in a mixture. So suppose you have a sample which is made up of different components, and you want to isolate or extract these components separately from it, then you will use this technique, which is called chromatography. Now, before we go further, let's see the terminologies first. So, first is mobile phase. So, mobile phase is a solvent that flows through the supporting medium. So, basically, um, this is more or less like a transport medium, which takes your component or mixture that you want to separate together with it and helps in separation. Then comes the stationary phase. So stationary phase is basically a, material which is packed into the column, layer or coating. This is also a supporting medium that interacts with the mobile phase and the component that are dissolved into it, and it binds or interacts with it and helps in the separation of the components. Now,
Sorry,
yeah,
Dr. Saurabh, these slides are not moving. And I think you can stop slideshow. That will work, I think, because the slide is not clear. It's not clear.
I didn't change the slide, that's why it didn't move.
Okay, okay then. Uh, but I
Yeah,
suggest you stop slideshow because slide cut हो रहे हैं.
okay. Uh, I'll try to maximize the slide so that it is still visible. The slide is completely visible, right?
Actually cut.
It is quite zoom, sir.
Uh, yeah,
You need to minimize it. I mean, you can stop slideshow. That will work.
no, I already stopped the slideshow. So it's not on slideshow. Yeah, yeah, sometimes Zoom doesn't work properly. Now somehow it,
That's good. Yeah,
oh,
fine.
okay, now I get what the problem is. So basically it has to be in this bar that has come.
Okay.
Just give me a second, I'll adjust it accordingly.
No problem.
Yeah. So yeah, so we were discussing about the terminology. So the third one is supporting medium. So a solid surface on which this stationary phase is bound or coated, that is the supporting medium. So it could be a column in this case. So now we'll talk about the principle of chromatography. So now, based upon the stationary phase or the mobile phase, the principle or and the principle, chromatography can be classified into various types. So based on the mechanism of separation, it can be of four types. So first one is absorption chromatography. It works on the principle of absorption. Here the analyte molecule absorbs on the resin. So the resin is the material or the stationary phase that is filled in this column. So can you see the cursor?
Yes, sir.
Yeah.
Yes,
So
sir.
here is a typical example of a column chromatography, a column chromatography, and this is a column. So the material that you see filled from here to here is the stationary phase, and so basically in absorption chromatography, the component that you want to isolate or separate, the analyte molecule that binds temporarily to this stationary phase. The examples of this type of chromatography is affinity chromatography or HPLC, high performance liquid chromatography. Then the other chromatography, second, is partition chromatography. So what happens in partition chromatography is that the separation is on the basis of sample partition due to its solubility in liquid or mobile phase. So depending upon how soluble the solute or the component is in the mobile phase, this chromatography works. The third one is the ion exchange chromatography. So in ion exchange chromatography, there is an, yeah, uh, any question or something? I assume no. So in ion exchange chromatography, there is an exchange of ions. That is, ions are attached with the resins that are present in the stationary phase of the resins and the ions in the sample. So basically the ions that are present in the component or the sample that you want to separate, they form a temporary bond with the stationary phase resin. Or so when you add your analyte, then the ions that are present in the analyte, they replace the ions that are already present on the resins and they bind themselves in their place. So they basically replace themselves with the existing ions. And when you change the buffer conditions, then the components that you wanted to separate that were bound to the stationary phase, they get eluted, and this is how you do the isolation separation in this case. Then the fourth type of chromatography here is size exclusion chromatography. So in size exclusion chromatography, the separation is based on size of the component to be isolated. This is also called as gel permeable chromatography. Why? Because uh, it depends on the size of the molecule. So what happens if you have a packed matrix or a packed stationary phase, then the smaller the size of the particle will be, the faster it will go through it. Whereas the bigger size of the particle, it will get stuck and it will move slowly into the column. So similarly, if we talk about other types of classification, then classification can also be done on the basis of mobile phase. Uh, Sorry, I forgot to change the slide. So classification can also be done on the basis of mobile phase. So mobile phase can be liquid, gas, or supercritical fluid. Solid mobile phase is not possible because, of course, solid mobile phase will not move. So the only mobile phase that is possible is liquid chromatography, or a gas mobile phase in gas chromatography, or supercritical fluid in supercritical fluid chromatography. Now, in liquid chromatography, the mobile phase that is used is liquid. Of course, it suggests in the name. For example, uh, in normal chromatography or reverse phase chromatography, or for example, hydrophobic or hydrophilic interaction chromatography, then ion exchange chromatography, and so on. In gas chromatography, the mobile phase that is used is gas. And in supercritical fluid chromatography, the mobile phase that is used is a supercritical fluid. Now, what exactly is a supercritical fluid? Supercritical fluid is a substance above its critical temperature and critical pressure. So basically, it's uh, a liquid which above its critical temperature and critical pressure can exist in a liquid or a gaseous phase. So an example could be carbon dioxide. Now, then if we go further, then this chromatography can also be classified on the basis of stationary phase. So stationary phase can be solid and it can also be liquid. So here now depending upon how the resin is present, it could be planar or column chromatography. So planar chromatography, here the resin or the separation bed where the separation has to take place is on a planar substrate. Example is your TLC paper chromatography, where liquid molecules are dried on a planar surface. And TLC, for example, thin layer chromatography, where silica gel is dried on a glass or an aluminium surface. Then the other one is column chromatography. So in column chromatography, the stationary phase is packed or filled in a column, in a tubular column. For example, ion exchange chromatography, then HPLC, then hydrophobic interaction chromatography, and so on. Now, this column chromatography can also be of two types. So one is packed column chromatography and the other one is tubular column chromatography. So packed column chromatography, the examples are HPLC and affinity chromatography, whereas tubular column chromatography, where the column is a tube or a coil-like structure, the example there would be gas chromatography. Now, there are various types of chromatography that we just discussed. So just to name them, we have normal phase chromatography, reverse phase, then hydrophobic interaction, where hydrophobic interactions takes place between the stationary phase and the analyte molecule. Then this hydrophilic interaction. So there is a hydrophilic interaction that takes place between the stationary phase and the analyte molecule that you want to isolate. Then ion exchange, where there are ions in your component that you want to separate, and the stationary phase also has ions. So basically there is a temporary replacement of ions of the component molecule with the resin or the stationary phase, and further when you elute it, then you get the separation done. Then fast protein liquid chromatography, here you use it to separate proteins. Then size exclusion chromatography, where separation is on the basis of size. Then comes affinity chromatography. So this is also very frequently used kind of chromatography. And here what happens is there is an interaction between the component and the stationary phase. So basically this is used when you have to isolate or purify a protein. Say for example, the antibody purification that are done. So what you do is you use a antigen or some molecule that has affinity for the antibody, and then you pack the column with it. So when the lysate with the antibody is flown through the column, then it forms a bond with the antigen, and this is how it gets holed up into the stationary phase of the column. And further you change the condition like pH, temperature, or solvent conditions, and then you elute the antibody. Then supercritical fluid, where we use supercritical fluids like carbon dioxide to do the separation. Then gas chromatography, here the mobile phase is gas, and it's the stationary phase is packed into a coiled column structure. Then paper chromatography, which is a planar type of chromatography. Same is the case with thin layer chromatography and so on. So now that you have the basics of chromatography, now we can go into HPLC. So if there is any question thus far, you can ask. If not, you can say no.
No, sir.
No question, sir.
Yeah, okay.
No, sir.
Then we'll move to HPLC. So HPLC is high performance liquid chromatography. This technique is basically used for separation, identification, and quantification of the component from a mixture of component. So suppose you have a mixture of component which has different types of components in it. So to isolate or separate a single component from it and identify if it is a protein molecule or a phytocompound or something else. Then if you also want to quantify it, then the technique that you will use is HPLC. Now, HPLC is a type of liquid chromatography only, and it uses phase, liquid mobile phase. And HPLC is also called as high performance liquid chromatography. Why? Because the resolution power of HPLC is very high. Now, resolution power, what do you mean by resolution power? So resolution power means the ability to distinguish between two components. So if you say, for example, for your mixture has two components, so the ability of the system to separate those two components effectively is basically the resolution power of the instrument. Now, this resolution is due to the reason that it is most preferred method that is used in the lab nowadays. Now, HPLC basically purifies or separates on the basis of polarity of the components, where polarity is basically the tendency of a molecule to like or dislike water, like hydrophilic or hydrophobic, you must be knowing. So if a molecule is polar, then it likes water and it's hydrophilic in nature. While if that molecule is hydrophobic or non-polar, then it is not water loving, it's water hating. So this HPLC also is called as high pressure liquid chromatography. Now, why it is called high pressure? Further in the presentation, I will tell you about the column. So what happens in HPLC is the column, the analytical column that is used for the separation of component, that is packed very um, tightly. It's very nicely packed. So that's why it's very difficult for the solvent or the components to go through it. And this is why a high pressure is applied so as to push your mobile phase along with the component through that column. And due to this, a rapid separation of the component is done, and also a effective separation of the component is done. Approximately 1000 to 4000 psi is the pressure that you can that you apply usually in HPLC. So now with this done, uh, let's talk about the components that are used in HPLC. So basically, HPLC also has a stationary phase. So in HPLC, there is a column which is a tube-like structure filled with a solid absorbent material tightly packed. So this stationary phase is tightly packed with resins, or I will tell you later that this stationary phase is silica. So it is tightly packed with silica. Now, tight packing of the column is very crucial for effective separation. Why? Because if it is not tightly packed, then there will be air pockets or air gaps, and that will cause hindrance in the effective separation of the components. Then silica is an example of hydrophilic solid absorbent material that is used in normal phase HPLC. So what is a normal phase and what is a reverse HPLC, that reverse phase HPLC, that I will tell you in the next slide. And in reverse phase HPLC, we use this silica, a modified version of silica. So what we do is we attach a 18 carbon chain that makes this silica hydrophobic in nature, and thus we can use it in reverse phase chromatography, HPLC. So both the sample and the mobile phase passes through this column. The grain size of the particles that are present in the column, which are packed into the column, is around 3 to 5 microns in diameter. Now, the second thing that we use here is sample. So sample can be anything like blood or bacterial toxin, or for example, fungi or toxins from fungi, or a mixture of protein or some other plant extract that you want to separate the components of using a HPLC. Then the third thing that is there is mobile phase. So mobile phase, as the name suggests, high performance liquid chromatography. So mobile phase has to be a liquid. So this mobile phase basically consists of approximately 90% of water and 10% of organic solvent, because the component that you want to separate, it may or may not have something that is soluble in water, and it may also have something that is not soluble in water and may be soluble in organic solvents. So now this mobile phase is hydrophilic because it contains 90% of water. So this mobile phase is hydrophilic. Later in further stage, a concentration gradient is also used. So initially, when you start a HPLC, you used a mobile phase which is hydrophilic in nature and has around 90% of water. Now, as the process continues, you start decreasing the percentage of water and start increasing the percentage of organic solvent up to a limit of 90%. And when the organic solvent is around 90% or something, then the complete column cleanup will be done this way. So the whole, every component that was present in your mixture will be eluted out. Now, uh, uh, so the individual component in the sample that are present, they are basically separated on this stationary phase packed into the column, and then under the influence of pressure, it is pushed using a mobile phase out of the column. The component that leaves the system is called eluent, and from the column it goes directly to the detector where the detection is being done, and a readout is generated in the form of a graph which is called as a chromatogram. Now, technically, LC, that is liquid chromatography, and HPLC both work in the same way, because this HPLC is an advanced version of LC only. Just you have to apply a high pressure. So what enhancement it does is it gives you speed, better efficiency in of separation, high sensitivity, and ease of operation. Now, the theory behind HPLC. So basically, HPLC is dependent on one diameter equation of rate theory. So here HETP is equal to A plus B by mu plus C of stationary phase plus C of mobile phase times mu. So now HETP is basically the height equivalent to the theoretical plate, and it is the minimum height that is required for equal distribution of analyte between the stationary phase and the mobile phase. Then the A here is the eddy's diffusion on, or the multi-path effect. So basically there is a multi-path. So I'll explain about this also further. So then B is the longitudinal diffusion, and C is the mass transfer rate. Then mu is the flow rate of the mobile phase. Now, eddy diffusion or the multi-path effect, as the name suggests, that there are uh, multiple paths that will be available in the column or plate, due to which peak broadening will take place. Now, peak broadening, as in when the when the component starts to elute from first, say for example, from first second your component starts to elute. So it will take some time to elute that component completely, and because of which there is peak broadening. It does not comes in out in a sharp peak. So that is there. So that is eddy's diffusion or multipath effect. For example, in a column or a plate that is fitted with stationary phase of varying size, a single analyte will have different path or different length um, to come out of the column, and this is due to interparticular spaces, how beautifully or how tightly the column is packed. So this will this basically is the thing that is responsible for peak broadening. Now, uh, longitudinal diffusion. In longitudinal diffusion, the mobile phase, uh, yeah, a mobile phase is diffused longitudinally, thereby causing turbulence effect. That is, there would be higher concentration of solute in the middle, whereas lower concentration at the edges. So basically in the middle, the solution will run faster, whereas towards the wall, it will be slow. And in liquid phase, the diffusion is less, but in gaseous phase, the diffusion is more. Thus, this component will be negligible in the case of high performance liquid chromatography. Now, mass transfer rate depends upon the affinity between the stationary phase and the analyte, affinity between the mobile phase and the analyte, as well as the flow rate of the mobile phase. Now, low flow rate gives good separation, whereas higher flow rate will uh, give you a fast separation. Now, types of HPLC. So basically, depending upon the relative polarity of the solvent and the stationary phase, there are two variants in HPLC. One is normal phase HPLC, and the other one is reverse phase HPLC. So in normal phase HPLC, a polar absorbent substance surface is used and a non-polar eluent is used. Whereas in reverse phase HPLC, a non-polar absorbent surface is used and a polar eluent is used. Now, in normal phase, polar substance in the mixture stick to the polar absorbent. Then non-polar, and hence non-polar substance will leave the column first. So basically the polar absorbent sticks to the polar substance that are present in the mixture that you want to separate out, and the non-polar, since it does not stick to the matrix or the stationary phase, it moves out first from the column and it gets separated first. Whereas in the reverse phase, non-polar compounds in the mixture, they get attached to non-polar absorbent, that is the stationary phase that is present in the column, and hence the polar molecule which are not bound to anything leaves the column first and get separated. So reverse phase HPLC is the most commonly used form of HPLC nowadays in the lab. Now we'll talk about the instrumentation. So this is the block diagram of HPLC. Now coming to different parts of HPLC. First, we'll talk about solvent reservoir. So if you can follow my cursor, then I can show you what exactly it is. So these are the solvent reservoirs. Solvent reservoir is used to store the solvent in HPLC. In HPLC, there are two kinds of solvent or two types of solvent reservoir systems. One is a binary system and the other one is quaternary system. Binary system consists of two bottles or two reservoirs. Like this flow chart here, we show two solvent systems. So basically, this is a binary type of system where, whereas if we had four solvents here, then it was a quaternary system. Now, in HPLC, the solvents that are used are HPLC grade and are highly pure, and they are ought to have no foreign particles and free of impurities. So once we have this binary or quaternary reservoir system, the solvents, they move to degasser. Now, what exactly is degasser? Here you see the degasser. There will be separate degassers for separate solvent bottles. So degasser is used to remove the dissolved gases in the mobile phase or solvent. Uh, This degassing is done using a vacuum pump, uh, which removes the gases from the solvent. Now, why degassing is required? Degassing is required because degassing will give better separation. Otherwise, what will happen if there are dissolved gases in the solvent? Then, when it goes to the analytical column, where the pressure will be very high. So, what happens at high pressure? Air bubble and gas molecules that are present in mobile phase will come out of the solvent, and they will get trapped into the matrix or the stationary phase of column, thereby causing a improper or ineffective separation. So then the third thing that we come is across is solvent mixing vessel. So now, um, I told you in the previous slide that the solvent that we use is a mixture. So 10% of organic solvent and 90% of water. So now from solvent one reservoir bottle, say for example, you get water, and solvent two reservoir gives you organic solvent. So you have to mix it. So this is the mixing vessel that is used to mix these liquids that are coming from these solvent bottles. Now, further, we come across a high pressure pump. Now, why a pump is used? To push this mobile phase into the column under high pressure. Why? Because the column of HPLC is very tightly packed, and it is very hard to pass through it. Thus, a lot of pressure is required to push the mobile phase through the analytical column. Now, there are basically two types of pumps that are used in HPLC. One is constant pressure pump. This constant pressure pump will provide with a constant pressure. And the other one is constant flow rate pump that provides with a constant flow rate. Generally, we use a flow rate of 1 ml per minute, and this is how a better separation is done. So basically, a constant flow rate pump gives a better separation compared to a constant pressure pump, because in constant pressure pump the flow rate is not constant, only the pressure is constant, and thus due to changes in flow rate the separation gets hindered and effective separation is not achieved. Now, there is also a common problem that I want to discuss. So in HPLC, there is a very common problem called back pressure. And there are two types of back pressures. One is low back pressure that occurs in new columns, whereas the other one is high back pressure, which occurs in old columns. Now, why I'm talking about back pressure is because HPLC is an instrument that is very frequently used. So when you put a new column, then the new column is completely clean, and hence the pressure that you applied easily leaks out, and this situation is called as low back pressure. Whereas if you have an old column that is in under regular use, then what happens is, due to the blockage of the pores of the stationary phase or due to impure mobile phase that you are using, the column gets choked or blocked, and due to which there is a high back pressure created. Now, to avoid such kind of experimental errors, what we also do is we use a pre-column. This is a pre-column or a guard column. So the role of this column is to guard the analytical column. And how it does that? So the solvent that you want to send to your analytical column has to first pass through this pre-column, and this pre-column or the guard column will filter the mobile phase and remove any contaminant that is present in it. After that comes the sample injection port. So sample injection port is the port where you inject the component or sample that you want to isolate or purify. These are also three types of sample injection. So first one is a common one, that is septum injector. So septum injector is an injector where we inject the sample using syringe into an auto sealable septum. So basically, once you inject, it seals automatically. So that is a septum injector. The other one is stop flow septum less injector. So as the name suggests, stop flow. So you have to stop the flow of mobile phase. Then you have to insert or inject the sample using a valve. And once that is done, you will close the valve and then you'll restart the flow. The third one, or the most the modern injector you can say, is micro volume sampling injector. So this is basically a high accuracy injector, and it uses loop injection. So basically you fill the loop before starting the experiment, and then you start the experiment, and then just by changing the loop or the direction of the flow, you auto inject the sample or the component that you want to isolate. Now, this micro volume sampling injector also has the capability of auto injecting. So you can auto inject, you can program, and you can auto inject multiple um, analytes. Now, uh, coming to our next component. So next component is a analytical column. So analytical column is a tube-like structure that is tightly packed with small particles of size around 30 to 20 microns. And this is often made up of metal or sometimes very thick glass. And it has the capability to bear a pressure of approximately 14,000 to 15,000 psi. Then the next component that we have is a detector system. So the role of detector system is to monitor the components that are coming out from this analytical column, to analyze them and to identify what exactly it is. Now we'll talk about the components separately, and I'll just quickly give you a few take home lines about different components of HPLC. So HPLC pump. So this pump forces the mobile phase through the column at much greater velocity compared to the gravity flow. So in gravity flow, you let the separation happen under the influence of gravity, whereas in HPLC, you use this pump to provide a greater velocity, and thus a faster separation is done. Now, then these are different kinds of pump. So pneumatic syringe type pump or reciprocating pump. Then pumps can be multi-head pumps with two or more reciprocating pistons. So reciprocating pistons gives you a continuous flow. So say for example, if you have to run a particular instrument for a longer time and you have a lot of uh, components to be separated, then you will use a multi-head pump where continuous flow is maintained using two different syringes. Now, these pumps are usually designed to provide a stable flow, because if there is pulsation, then pulsation will cause ineffective separation due to varying pressure on the mobile phase. Now, usually the flow that we use is 0.01 to 10 ml per minute, but the standard is around 1 ml per minute. Then after this, the injector. So injector is the port from where you inject. So these are the typical examples of the injector. These are low. Say if you see this figure, this is the second type of injector, where stop flow septum injector. So basically you inject here and then you change the position of the valve. So the quality of the injector should be that it should produce minimum disturbance, and it should reduce peak broadening. Then these are different HPLC columns that are commercially available. This is from the company Hamilton, and these are different sizes and different pore sizes and different length of columns that are available. Then detectors. So as I told you, HPLC detectors basically monitor the elute that leaves the column. It produces electronic signal or readout proportional to the concentration of each separated component. And these detectors should have the following qualities, like um, it should be capable of doing crucial trace analysis. Then it should have a high sensitivity. It should be fast to response. uh, it simplifies quantitation. Then intensive to change. It should be insensitive to any change in the solvent or the flow rate or the temperature. So if the flow rate of like for example, if you used a constant pressure pump, then there will be changes in flow rate. So it should not give any response to changes in flow rate. It should also not be sensitive to changes in temperature or to solvent, because initially you will start with hydrophilic solvent, and later you will use a solvent gradient where you will shift more towards the hydrophobic solvents or the organic solvents. Now, types of detectors that are used. So basically, there are five main types of detector that are used in a HPLC. The first one is spectrophotometer. So it measures the absorbance of light, and the detection limit in which it works is in nanograms. So here, what is required is that the analyte that you want to separate out, that must absorb UV or visible light. The second type of detector that we use here is fluorometer. So fluorometer measures fluorescence, and the detection limit of fluorometer is in the range of picogram to nanogram, and the analyte must fluorescence. Then the third type of detector is electrochemical detector. So electrochemical detector basically works on the principle of electrochemically measuring the oxidation or reduction of the analyte. The range in which it works, the detection limit is around picogram to nanogram. And this is only the detector that are used for detection of catecholamines. Then refractometer. Refractometer measures the refractive index, the changes in refractive index, and these are sensitive in the range of micrograms. These are the normal detector that are mostly used uh, um, in school and colleges, where very high separation is not required. So detection of most compounds are done with this refractometer, but their sensitivity would be less. Now, the most important detector that we use in HPLC is mass spec or mass spectrometry. Now, this is used in mostly all the pharma and companies where pharma and medical phytocompounds isolation companies, where very effective separation is required, and then also identification of the molecule that is coming or analyte that is coming out is required. So there they use mass spectrometer as a detector. So it basically detects ion after separation by mass to charge ratio. So the range of detection is in uh, femtograms to nanograms. It's very, very sensitive. And here, what is required is that the analyte must be converted into a ionized form. Now, let's see a little bit about the working of HPLC as a whole. So this is the schematic of, uh, or rather the working of the instrument. So this is the instrument, how it looks. So now what I will do is I will inject uh, a sample. So here I injected this pink color component, pink color sample, which has multiple components. Now this will move in the column, and as soon as it started moving into the column, the stationary phase of course will reach the mobile phase will of course reach the detector already, because before starting HPLC we first run uh, blank mobile phase, so that the whole system gets calibrated and standardized. Now, once that is done, we do loop injection of the component that we want to separate. So as soon as the mobile phase reaches the detector, we start to get a stable line or the baseline. This is called as the baseline. Now, this is the component that we want to separate, and this is now moving. Now, this will enter the column. So, as soon as it started entering the column, separation will start taking place depending upon how it binds to the stationary phase in the column. In the next step, you see the 6 components that were present in the sample are getting separated, further separated, and now the first component that left the column has entered the detector, and here in the chromatogram, so this is the chromatogram, you see the first peak of this component that is present in the detector. Now, second component is in the detector and you see a second peak. Further, this is the last component and your chromatogram is almost complete. So here on this axis, you have the retention time. Now, what is the retention time? Retention time is a time that a particular component was retained into the column, or a particular time that the component that you want to separate or isolate stayed into the column. That is the retention time. Now, if you want to know the concentration, what is the amount? What is the amount of the solute that is present in your component? So what you will do is, say for example, if I want to know the amount of component of this peak, so what I will do is I will calculate the area of this peak, and with the area of this peak, I will be able to find out what was the amount of this component that was present in the component mixture. Now, this is oh, now that's a problem. So what I'll do is I will just remove this one a little bit and we'll talk about mass spec. So HPLC-MS. So where we use mass spectrometer as the detector for HPLC. So an analytical technique that basically combines the separation capabilities of HPLC and the mass analysis capabilities of MS. HPLC separates the mixture with multiple component, while mass spec provides the structural identifies the component that are present with high molecular specificity and detection sensitivity. Now, what mass spec does? Mass spec is an analytical instrument that measures mass to charge ratio of charged particles. So basically, in the presence of electric or magnetic field, MS, what it does is charge the particle and then it measures the mass to charge ratio. And because of this mass to charge ratio, we have a standard where we compare the mass to charge ratio that we obtained of a particular compound. And then this is how we identify that, okay, this is the compound that has come out of the column. Now, mass spec can be used to determine the mass of the analyte, uh, their elemental and isotopic compositions. This mass spec is also used to identify between, say, for example, if you have different carbon chains, say 16 carbons, 18 carbons, 20 carbons. So what you will use to identify, so you will first run it on a HPLC column, then they will get separated, and once they will get separated, you will use a mass spec detector to identify the isotope, the composition of the isotopes. Now this is the schematic of a mass spec. So basically HPLC-MS. So basically the first part, this is the first part, that is the HPLC. And then this is the analytical column. From this analytical column, the separated samples are injected into a LCMS. And this is the ionization chamber, where electric field and magnetic field are present, which ionizes the separated components that are present, and these are flown directly into the detector of the mass spec, and there it is, charge to mass to charge ratio is analyzed, and you get a graph like this, from where you can get the size and mass to charge ratio and identification of the compound that you were isolating, or that you were separating using a HPLC-MS. So yeah, that's more or less it is. So if you have any questions.
Good afternoon, sir. I have one question on HPLC chromatogram.
Yeah.
In case of HPLC chromatogram, we get a factor called tailing factor, right? Uh, Based on which we usually analyze what kind of a sample, I mean, how much amount of sample we have given. So in that, if the tailing factor happens to show some kind of a fronting or tailing, what can we do to overcome that experimental error? Because sometimes when we work with enzymes, we calculate the enzyme kinetics based on nanograms of product yield. So even though the error is very small, it has a larger implication on the kinetics.
Yeah. So basically, you want to isolate this enzyme using a HPLC, or what exactly you want to do?
No, sir. We have to quantify the product after the enzymatic reaction.
So you have to quantify the product. So yeah, how exactly you want to do it with HPLC? I mean, uh, HPLC is basically a separation technique. So you will separate the product. So basically what you are saying is, in an enzymatic reaction, when there are two components, so you add the whole thing onto a HPLC column, and then you want to see how much product is there and how much reactants are there. Is
Uh,
that what you want to say?
Yes, sir. In that, if, when we do that way, there
Yeah.
is a we have observed a factor in the tailing factor. We have observed fronting sometimes and tailing sometimes. So the
Yeah.
tailing factor varies. How
Yeah.
can we
So
overcome?
So basically, that is because of the reaction being in equilibrium. So what happens is, sometimes the product is more, sometimes the reactant is more, right?
Yes, sir.
So this is why you see this tailing effect. And as long as there is equilibrium reaction. So basically, if you want to see more of a product, then you have to shift the pH or the temperature of the system in such a way that more product is formed at a particular given time. Then only you will be able to remove this tailing effect.
Okay, sir.
Yeah.
Hello, sir.
Yeah.
So my question is, can we use multiple columns for a single run HPLC?
uh, well, in principle you can, but why you want to do that? I mean,
Means for the better separation.
but HPLC column, you already get a, better separation, because you so basically, yeah, there are many kinds of columns, so you have to choose a specific kind of column that will be best suited for your mixture component. So adding more number of columns is not a solution. So basically, if you have to do something like that, first of all, the system is not designed so that you can add multiple columns. So what you do is you run one HPLC, then if you want to run it through another HPLC round, then you change the column and run it again. So this is how you do it. You don't attach more than one column to it, because that will also cause an effective loss in pressure.
Okay, sir.
Yeah.
Any question now?
No, ma'am.
Okay, so Dr. Saurabh, I'm really grateful to you for your time and this wonderful session. It was really informative, and I think everything was really very clear. Those who never, used HPLC or never gone through that, but it was really useful for the students, because afterward they have to come here for hands-on training and they have to work on grassroots practices where they have to use HPLC as well as SPLC. So it will be really useful for them. Thank you so much for your time, and we always look forward for your support and guidance for this upcoming weeks.
Sure.
Thank you so much.
Thank you.
Okay, students, so we have next session at 2:30 by Dr. Vinay Shukla, who is a professor at Ayurvedic University, Gujarat Ayurvedic University. And please join before time, and he'll be taking lecture on HPTLC, which is actually must to learn. When you come here, you have to know and you have to handle the HPLC instrument for hands-on training. Okay, so please join that time, and after the session we will discuss about assignment 4. Okay.
Okay, ma'am.
Okay, ma'am.
Okay, ma'am.